There are places in the Milky Way where the night sky would no longer look like the one above Earth. From inside one of those places, the nearest stars would not be separated by the familiar emptiness sea between the constellations. They would gather in every direction, layered across the sky in numbers too large for the eye to sort. Some would shine close enough to cast faint shadows. Others would merge into a pale background of unresolved light, as though the cluster itself had become a second, crowded galaxy. These places are globular clusters. From Earth, many of them appear modest. Through a small telescope, a globular cluster may look like a rounded patch with a brighter center, almost featureless at first glance. Yet that blur can contain hundreds of thousands of stars, and in some cases far more, held together by their shared gravity inside a roughly spherical voltgrove of space. The stars become increasingly concentrated toward the center, where even powerful telescopes can struggle to separate one point of light from the next. NASA science. The Milky Way has about 150 known globular clusters. Unlike the younger star groups that travel mainly within the galaxy's flattened disk, many globular clusters move through the surrounding halo, passing above and below the spiral arms as they orbit the galactic center. They are not fixed decorations around the galaxy. Each cluster follows its own long path through the Milky Way's gravity, carrying an entire population of stars with it. NASA science too. Most of these clusters are immensely old. Their stars began forming billions of years before the Sun, during eras when the Milky Way had not yet settled into its present shape. Some clusters may have formed within the young galaxy itself. Others appear to have arrived inside smaller galaxies that were later drawn apart and absorbed by the growing Milky Way. Their present-day orbits, motions, and chemical patterns still preserve traces of those earlier systems. Science 3. That is why astronomers often treat globular clusters as records of galactic history. They are not records in the ordinary sense. Nothing inside them describes the past in words. Their evidence is carried in starlight, in color, temperature, motion, mass, and the abundance of elements heavier than hydrogen and helium. A star cannot remember where it was born, but its chemistry can retain something of the cloud that formed it. A cluster cannot explain how it entered the Milky Way, but its orbit can reveal that it does not move like stars born in the galaxy's main disk. And so the oldest star clusters offer a different way to enter the history of our galaxy. Instead of beginning with the Milky Way as it appears now, with its spiral arms and bright central band, we can begin with the surviving pieces that came before much of that structure was complete. We can move inward from the halo, from these compact gatherings of old suns, and ask what they have endured through more than 10 billion years of galactic change. Their stars have aged, some have swollen into red giants. Others have already left behind white dwarfs, neutron stars, or black holes. The clusters themselves have crossed the Milky Way again and again, losing stars, tightening in their centers, and being reshaped by every passage. Yet many are still here. To understand why, and to understand what they carry, we begin not with the galaxy's bright disk, but with the ancient systems moving around it. Far from the crowded band of the Milky Way, the constellation Hercules holds a faint object that can be found with binoculars on a clear night. It does not look like a city of stars. It looks more like a small patch of mist, rounded and pale, without a sharp edge. This is Messier 13, one of the best-known globular clusters in the northern sky. Its light has crossed roughly 25,000 years of space before reaching Earth. The cluster spans about 150 light-years and contains well over 100,000 stars, though from here nearly all of them blend into a single glow. A NASA science, the appearance changes as the distance closes. At first, the cluster remains a sphere of combined light. Then its outer stars begin to separate. Individual points emerge from the haze, scattered around the edges in long, irregular streams. Farther inward, the spaces between them narrow. The view grows brighter, not because any one star has changed, but because more stars now occupy each small region of sight. A globular cluster has no solid boundary. There is no surface to cross and no wall marking the moment of arrival. The outermost members mingle gradually with the wider stellar halo of the galaxy. Some remain loosely bound. Some are already being pulled away by the Milky Way. Only after traveling deeper does the cluster's shape become unmistakable, with its density rising toward a luminous central region. This concentration is one of the defining features of globular clusters. Gravity has spent billions of years rearranging their stars. Each member follows its own orbit through the cluster, continually responding to the combined pull of all the others. The whole system may appear motionless in a photograph, yet it is filled with stars moving along paths that cross, curve, and change. The stars do not orbit in neat rings as planets do around the Sun. There is no single flat plane and no simple sequence of lanes. Their motions point in many directions, creating a three-dimensional swarm held together by a shared gravitational field. Near the outskirts, the Sun might still have recognizable neighbors if it were placed there. The sky would be richer than ours, but darkness would remain between the stars. Toward the center, the experience would be different. In the densest regions, many stars can occupy a volume that would contain only a few stellar systems in the neighborhood around Earth. Hing and Tianwan. Even there, however, the cluster would not feel physically crowded in the human sense. Stars are small compared with the distances between them. A sun can pass relatively near another sun without their surfaces touching. Direct stellar collisions are more plausible in a globular cluster than in the region around Earth, but they remain unusual events. Most stars complete their long movements without ever striking another. Gravity still allows close encounters to matter. When two stars pass near each other, each can leave with a slightly altered speed and direction. One may give up a little energy while the other gains it. Across millions of encounters and billions of years, these tiny exchanges change the cluster from within. More massive stars tend to settle toward the center. Lighter stars are more likely to wander outward. A few can receive enough energy to escape the cluster entirely. The result resembles a system that is slowly sorting itself, though no intelligence and no central organizer guides the process. It is the cumulative outcome of gravity acting through countless small meetings. From a point near the core, the sky might contain bright stars in nearly every direction. Red giants would stand out with warmer light. Smaller main sequence stars would fill the background. Compact remnants, including white dwarfs and neutron stars, would remain mostly unseen, their presence revealed through motion, radiation, or the behavior of nearby companions. There might never be a fully dark night. That does not mean the sky would blaze like daylight. Much would depend on the exact location and on the kinds of stars nearby. But the familiar pattern of a few thousand naked-eye stars separated by broad black intervals would be gone. The surrounding cluster would build a deep field with the unaided eye, a layered view that Earth requires large telescopes to approach. It is possible to imagine standing beneath that sky, though the cluster may not be a welcoming place for a planetary system. Close stellar passages can disturb wide planetary orbits. Radiation from nearby stars may alter the environment around a world. In especially dense regions, a distant comet cloud or loosely bound outer planet could be vulnerable to repeated gravitational interruptions. Yet, conditions vary greatly from the cluster's outskirts to its center, and the long-term survival of planets within globular clusters remains an active area of study. For now, the important change is one of perspective. From Earth, the cluster is compressed into a soft point because distance removes its depth. From within, it would become an environment. The round shape seen through a telescope would disappear, just as the shape of a forest disappears when someone walks beneath its canopy. There would be no convenient view of the whole, only stars, motions, and the gravitational structure inferred from what the stars are doing. Astronomers face a related problem from Earth. They can photograph a cluster, measure its brightness, and follow the movement of many of its members. But a telescope presents a projection. Stars on the near side, stars in the center, and stars on the far side can appear beside one another in the same image. To reconstruct the cluster, researchers combine several kinds of evidence. Star's position shows where it appears on the sky. Its proper motion reveals its gradual sideways movement. Shifts in its spectrum show whether it is approaching or receding. Brightness and color help identify its temperature as the stage of life. Gaia has measured the motions and properties of immense numbers of stars across the Milky Way, while Hubble has resolved crowded cluster regions where separate points can otherwise blur together. These observations allow globular clusters to be studied not only as pictures, but as moving systems with depth, internal structure, and long histories. Akakwan Vu Tru Cho. The mist in Hercules is therefore not a static ornament. It is a population in motion held in a sphere without a surface, shaped by encounters too small to notice individually and powerful enough to transform the cluster over time. What appears from Earth as a compact gathering is also a patient gravitational process. And within that process, the ages of the stars are waiting to be read. The ages of globular clusters cannot be read from a single star. A red giant may look old, but its color alone does not reveal when it formed. Even a star that appears almost unchanged can hide a history measured in billions of years. The answer emerges only when many stars are considered together. A globular cluster is especially useful because most of its stars are broadly understood to have formed during the same early period and from related clouds of gas. They do not all have the same mass, and they do not all evolve at the same rate, but they began their lives close enough in time that the cluster can be treated as a shared experiment. Their different masses allowed time to reveal itself across the whole population. Astronomers arrange the stars by brightness and color. The result is called a color magnitude diagram. It places hotter, bluer stars on one side and cooler, redder stars on the other, while showing which are bright and which are faint. The diagram is closer to a map of stellar lives than a picture of the cluster. Across much of that map runs the main sequence. These are stars still fusing hydrogen in their cores, including stars that resemble the Sun and many others that are smaller, cooler, and dimmer. A star's position along the main sequence is strongly related to its mass. Massive stars burn through their fuel quickly. Lower mass stars use it at a slower rate and remain in this stable stage much longer. This difference creates one of the most reliable clocks in astronomy. In a young star cluster, the main sequence extends upward toward hot, bright, massive stars. In an old cluster, those stars are gone. They exhausted the hydrogen in their cores long ago and moved into later stages of evolution. The most revealing place in the diagram is the point where stars begin leaving the main sequence. Astronomers call it the main sequence turnoff. The mass of the stars at that turnoff indicates how much time has passed since the cluster formed. If relatively massive stars are only now beginning to leave the main sequence, the cluster is young. If even stars only a little more massive than the Sun have already moved away from it, the cluster must be much older. For many globular clusters, the turnoff points to ages of roughly 10 to 13 billion years. That places their birth in the early history of the universe, long before the Sun formed and before the Milky Way had acquired its present structure. The universe itself is about 13.8 billion years old, so the oldest globular clusters belong to a time when galaxies were still assembling from smaller systems and large reservoirs of gas. Distance affects how bright the stars appear. Interstellar dust can make them look redder and fainter. The chemical composition of a star influences its temperature, luminosity, and rate of evolution. Models of stellar interiors must account for how energy moves outward, how material mixes near the core, and how helium and heavier elements alter the star's path through time. Small uncertainties in these ingredients can shift the age assigned to a cluster. Astronomers therefore compare several forms of evidence. They measure the turnoff. They study the shape of the subgiant branch, where stars begin expanding after core hydrogen is depleted. They examine the horizontal branch, where older stars burn helium in their cores. They use white dwarfs, whose gradual cooling offers another clock. They compare clusters with one another and place their results beside estimates for the age of the universe. Agreement among different methods gives the result its strength. The stars also carry a chemical clock, though it tells a more complicated story. In astronomy, every element heavier than helium is commonly grouped under the word metals. The earliest universe contained almost no metals. It was dominated by hydrogen and helium, with only traces of a few light elements. Carbon, oxygen, iron, and the other materials familiar on Earth were produced later inside stars and during stellar explosions. Each generation of stars returns some of those elements to space. New stars forming from that enriched gas began with a larger share of heavy elements than the stars that came before them. Because of this gradual enrichment, a star with very little iron often belongs to an old population. Many globular clusters are metal poor, which supports the conclusion that they formed early. But age and metallicity are not identical. A star can be metal poor because it formed early, or because it formed in a small galaxy where chemical enrichment proceeded slowly. Two clusters with similar ages may have different chemical compositions. Two clusters with similar metallicities may have arrived in the Milky Way by different paths. These distinctions allow globular clusters to become more than clocks. They become tracers of origin. Some clusters move in orbits and carry chemical signatures consistent with formation inside the early Milky Way. Others appear connected to dwarf galaxies that were captured and pulled apart. The clusters survived even after the larger systems around them dissolved into the galactic halo. Their stars now pass through the Milky Way as compact evidence of mergers that happened billions of years ago. The story became more complex when astronomers learned that many globular clusters are not made from one perfectly uniform generation of stars. Earlier models often treated each cluster as a simple stellar population, formed at nearly the same time from gas with one chemical composition. That approximation remains useful, especially for understanding the broad shape of a color magnitude diagram. Yet careful observations have revealed multiple stellar populations within many clusters. Stars in the same cluster may show varying amounts of helium, carbon, nitrogen, oxygen, sodium, and other elements. Their positions on precise color magnitude diagrams can separate into parallel sequences. In some clusters, the pattern suggests that star formation or chemical processing continued long enough to leave distinct groups behind. How this happened is still debated. One possibility is that an early generation of stars altered the remaining gas through winds, mass loss, or other forms of enrichment, and that later stars formed from material mixed with those products. Massive stars, rapidly rotating stars, and certain evolved stars have all been considered as possible contributors. Each explanation faces difficulties involving timescale, mass, and the cluster's ability to retain gas. The old image of a globular cluster as one population born in one brief event has therefore given way to something richer. The stars are still closely related, but not always identical in origin. The clusters may have experienced more than one episode of star formation or inherited chemical differences during its assembly. Its present simplicity from a distance conceals a more layered beginning. This does not make globular clusters less useful. It makes them more informative. A cluster's diagram can reveal when its stars left the main sequence. Its spectra can show what elements were present when they formed. Its internal variations can preserve the effects of early stellar activity. Its motion through the galaxy can hint at whether it formed here or arrived within another system. Age, chemistry, and orbit become parts of the same record. Consider what it means for one cluster to contain stars that have been shining for more than 12 billion years. Their light began long before Earth existed. They continued through the formation of the sun, the cooling of the planets, the first oceans, and the entire history of life on this world. Human observers entered only at the far end of that timeline. For generations, people saw globular clusters as faint objects in the night sky without knowing what they were. Larger telescopes gradually resolved their outer stars. Photography recorded stars too faint for the eye. Spectroscopy uncovered their chemistry. Space telescopes separated crowded cores, and precise astrometry added motion to the picture. Each method opened another part of the same old archive. The stars did not preserve the past by remaining unchanged. They preserved it by changing according to physical laws that can be understood. Their temperatures shifted, their cores exhausted one fuel and began another. Their outer layers expanded, their remnants cooled. The pattern of those changes is what allows time to be measured. Inside an ancient cluster, the past is not hidden behind the present. It is distributed across it. Some stars remain on the main sequence, burning at a pace slow enough to outlast nearly everything around them. Others have become red giants, bright because their internal structure has changed. White dwarfs carry the fading heat of stars whose outer layers are gone. Neutron stars and black holes remain as compact traces of the most massive cluster members from long ago. All of them belong to the same gravitational gathering, and when their light is arranged carefully, star by star, the cluster begins to reveal not only how old it is, but what kind of universe existed when it was young. There is another clock inside a globular cluster, one that does not depend on the fuel inside a star. It is kept by gravity. Every star in the cluster is moving. Some travel inward, some outward, and some pass through the center before curving back toward the edge. Their paths are not fixed forever. Each close passage by another star changes the motion by a small amount, and over long spans of time, those small changes accumulate. Astronomers call the process two-body relaxation. The name can sound simpler than the reality. A globular cluster may contain hundreds of thousands of bodies, all pulling on one another at once. Yet the lasting changes often arise through a long sequence of encounters that can be understood as pairs passing near each other, exchanging a little energy and continuing on altered paths. Most of these encounters are distant enough that neither star is harmed. There is no impact and no visible flash. One star merely leaves the meeting slightly faster, while the other leaves slightly slower. Repeated across the cluster, this exchange tends to move the system toward a more even distribution of kinetic energy. Massive stars do not need to move as quickly as lighter stars to carry the same kinetic energy, so the heavier bodies gradually settle toward the central regions. Lower mass stars are more easily pushed outward. This is known as mass segregation. It helps explain why the center of a mature globular cluster can contain an unusual concentration of heavy objects. The most massive ordinary stars from the cluster's youth are already gone, but their remnants remain. White dwarfs, neutron stars, and stellar mass black holes can drift inward through repeated gravitational encounters. The process does not happen all at once. A cluster is too large, and the spaces within it are too wide for rapid rearrangement. Depending on the cluster, relaxation may require hundreds of millions or billions of years. Globular clusters have had enough time for that patient sorting to become one of their defining features. The outer regions change as well. A low-mass star that gains energy can move into a wider orbit around the cluster. Another encounter may push it farther. Eventually, it can approach the boundary where the cluster's gravity competes with the tidal field of the Milky Way. Beyond that boundary, the star may no longer return. It becomes part of the galactic halo, carrying the chemistry of its birth cluster into a much larger orbit. Over billions of years, a globular cluster can lose a substantial share of its original population this way. Some of the stars now moving alone through the halo may once have belonged to dense stellar families that have since grown smaller or vanished. The escape of stars changes the cluster that remains. Energy leaves with some members and is redistributed among others. The central region can become denser. Stars that were once separated by greater distances begin passing one another more often. A feedback develops in which the core contracts, encounters increase, and the internal evolution of the cluster accelerates. This path can lead toward core collapse. The term does not mean that every star falls into one object. It describes a gradual concentration of the cluster's central region. As stars in the core transfer energy outward, the core loses support and contracts. The contraction raises the density, creating more encounters and allowing still more energy to move away. A familiar system might cool and expand when it loses energy. A self-gravitating system can behave in the opposite way. As the core loses energy and contracts, its stars move faster. Gravity converts the contraction into additional kinetic motion, so the central region becomes hotter in the dynamical sense, even while it continues giving energy to the outskirts. This unusual behavior is sometimes described as negative heat capacity. It is one reason globular clusters cannot be understood as simple collections of independent stars. The system responds to energy loss through the structure of its own gravity. The core tightens while the outer parts expand. One region becomes more crowded as another becomes more diffuse, but contraction does not necessarily continue without interruption. Binary stars can change the outcome. A binary contains two stars bound closely to each other. The pair stores orbital energy in its internal motion, and when another star passes nearby, a complicated exchange can occur. The visitor may leave with additional speed. The binary may tighten, becoming more strongly bound. In effect, the binary releases some of its orbital energy into the cluster. Across many encounters, hard binaries can act as an internal energy source. They can slow or reverse the contraction of the core, supporting it against deeper collapse. Astronomers sometimes call this binary burning, though nothing is burning in the nuclear sense. It is gravitational energy being transferred from tight stellar pairs to surrounding stars. The name captures the role these binaries play. They are small reservoirs hidden within the larger cluster, giving up energy encounter by encounter. A single meeting can produce several outcomes. The incoming star may be thrown outward. One member of the binary may be exchanged for a heavier visitor. Two separate binaries may interact and leave in new arrangements. In rare cases, stars may be driven close enough to merge. The crowded core therefore becomes a place where stellar lives can be redirected. A star in the galactic neighborhood around the Sun usually evolves according to its birth mass, with little interference from other stars. Inside a globular cluster, companionship and collision can alter that path. A star may gain material from a partner. A binary may be hardened by passing objects. A compact remnant may capture a companion and begin drawing gas from it. These interactions produce objects that would be difficult to explain through isolated stellar evolution alone. Blue stragglers are among the most visible examples. On a color magnitude diagram of an old cluster, they appear bluer and brighter than the main sequence turnoff. They seem younger than the population around them, as though they formed after the rest of the cluster. Yet globular clusters usually contain little cold gas for new star formation. The leading explanations involve rejuvenation through interaction. Two stars may merge, creating one object with more mass and a renewed supply of hydrogen available for core fusion. Or a star may receive matter from a companion in a binary system. In either case, the resulting star moves to a position on the diagram normally occupied by a younger, more massive star. The blue straggler has not reversed time. Its internal conditions have been rearranged. Other encounters reveal themselves at wavelengths the human eye cannot see. A neutron star paired with an ordinary star may pull material into a hot disk, producing X-rays. A white dwarf in a close binary can also become an X-ray source. Pulsars may be spun up by material transferred from companions, rotating hundreds of times each second with remarkable regularity. Globular clusters contain far more millisecond pulsars per unit mass than the wider galactic field. The dense environment makes the binary encounters needed to create them much more likely. A neutron star may begin by rotating more slowly. If it acquires matter from a companion, the incoming material carries angular momentum and spins the neutron star faster. After the transfer changes or ends, the object can remain as a rapidly rotating pulsar, sending beams of radio emission across space like the turning light of a distant beacon. Some clusters contain many of these compact clocks. Their pulses allow astronomers to measure orbits, test gravitational effects, and probe the distribution of mass inside the cluster. Small irregularities in timing can reveal companions that would otherwise remain invisible. The cluster's darkest members begin to show themselves through the motion of objects around them. Stellar mass black holes may also collect toward the center. For many years, researchers debated whether most black holes would quickly eject one another from globular clusters. Because they are heavy, they sink inward, form pairs, and undergo strong encounters. Those encounters can give black holes enough speed to escape, yet observations and simulations now support a more varied picture. Some clusters can retain black holes for billions of years. They may form binaries with ordinary stars or with other black holes. Encounters can harden those systems until gravitational interactions eject them, or until two black holes are left close enough to merge much later. Globular clusters are therefore possible contributors to the population of merging black holes detected through gravitational waves, although the origin of any individual merger is often difficult to determine. The central regions may hold another unresolved question. Some astronomers have searched for evidence of intermediate mass black holes, objects heavier than stellar remnants, but lighter than the massive black holes found in galactic centers. A compact concentration of unseen mass, rapid stellar motions near a core, or unusual radio and X-ray behavior can suggest such an object. But these signs can have other explanations. A group of stellar remnants can imitate the gravitational effect of one larger body. Crowding makes stellar motions difficult to measure. A proposed signal may weaken when better observations arrive. Several clusters remain candidates, but the evidence is not uniform, and no single claim should be treated as settled simply because the core is dense. The uncertainty is part of what makes these systems useful. A globular cluster is old enough for gravity to have run many experiments within it. Some experiments end in escape. Some create binaries, some exchange companions, some produce stars that appear younger than their neighbors. Some gather remnants into the center, where their presence can be inferred only through the movements of visible stars. And all of this happens while the cluster crosses the Milky Way. From the outside, it may still appear almost unchanged from one human generation to the next. The rounded glow keeps its shape. The same bright red giants mark the image. The same core seems to sit at the center. But on the scale, the cluster knows nothing is fixed. Stars pass and trade energy. Heavy bodies settle inward. Light stars migrate toward the edge. Binaries tighten. Remnants find companions. Some members are thrown away, and the sphere continues with fewer stars than before. A person watching through a telescope tonight sees only one instant in that process. The cluster itself has been rearranging for longer than Earth has existed, and gravity has never stopped counting. The Milky Way does not hold a globular cluster in isolation. Beyond the cluster's own gravity lies the much larger pull of the galaxy. The central bulge, the disk, the halo, and the unseen mass surrounding them all contribute to a field that changes from place to place. As a cluster moves through that field, the galaxy pulls more strongly on the side that is nearer and less strongly on the side that is farther away. That difference is called a tidal force. The same general principle raises ocean tides on Earth, though the scale and setting are different. The Moon does not simply pull the entire Earth in one direction. Its attraction varies across the planet, stretching the oceans slightly along the line between the two worlds. A globular cluster experiences a comparable difference across its own width, not from one nearby moon, but from the mass of an entire galaxy. Near the cluster's center, stars remain tightly held. Farther out, the cluster's grip weakens. A star near the edge may feel only a small difference between the pull of the cluster and the pull of the Milky Way. Given enough time, that difference can decide whether the star returns or begins a separate journey around the galaxy. The boundary is not a physical shell, it shifts as the cluster moves. Some globular clusters follow broad orbits that carry them far into the galactic halo before bringing them inward again. Others remain closer to the central regions. Their paths may be elongated, tilted, or even opposed to the general rotation of the disk. Gaia measurement have allowed astronomers to reconstruct many of these motions by combining the tiny sideways drift of cluster stars with their movement toward or away from Earth. Kekuan View True Choo, an orbit that looks smooth from a distance, can be demanding for the cluster itself. When the cluster is far from the galactic center, the surrounding gravitational field may be comparatively weak. As it falls inward, the pull grows stronger. The tidal boundary contracts, and stars that once remained securely attached can find themselves close to escape. Then the cluster may pass through the Milky Way's disk. The galactic disk is thin compared with its width, but it contains stars, gas, dust, and a large share of the galaxy's visible mass. A globular cluster moving through it encounters a rapid change in the gravitational field. Stars within the cluster receive a small jolt in their motions. Astronomers call this disk shocking. The word shock does not necessarily imply a collision with gas or stars. Most cluster members pass through the disk without striking anything. The disturbance comes from gravity changing over a relatively brief interval. Each passage adds a little energy to the cluster, especially to stars in its outer regions. A close passage near the central bulge can produce a similar effect. There, the gravitational field becomes stronger and changes quickly along the orbit. Repeated disk bulge passages can loosen a cluster over billions of years, helping the Milky Way remove stars one by one. The escaping stars do not scatter randomly. They continue to orbit the galaxy on paths very similar to the path of their former cluster. Some move slightly ahead, others fall slightly behind. Over time, they form two extended trails, one leading the cluster and one following it. These are tidal tails. At first, the tails may remain difficult to distinguish from the wider halo. Their stars are faint, spread across large areas, and mixed with unrelated foreground and background objects. But members of a tidal tail share several clues. They move in similar directions. They follow related orbits. They often carry chemical patterns consistent with the cluster from which they escaped. When those clues are combined, a cluster that once looked like a compact sphere can be seen as the bright surviving center of a much longer structure. The globular cluster, Palomar 5, offers a clear example. It is sparse compared with the dense, brilliant clusters that dominate telescope images, and the Milky Way has stretched its lost stars into long streams across the halo. The cluster is being dismantled gradually, leaving a narrow record of its orbit behind it. A stream like this is not merely debris. Its shape responds to the gravitational field through which it moves. If the Milky Way's mass were distributed differently, the stream would curve, widen, and develop gaps in different ways. Astronomers can therefore use stellar streams to examine the galaxy itself, including components that emit no light. Most of the Milky Way's mass is thought to reside in a halo of dark matter. Dark matter does not shine, absorb light in the ordinary way, or reveal a surface. Its presence is inferred from gravity, from the motion of stars and gas, the behavior of galaxies, and the structure of the universe on larger scale. Globular clusters and their tails become small spallist particles moving through that invisible landscape. A cluster's orbit can help estimate the galaxy's total mass. A thin stream can reveal how smooth or uneven the gravitational field is. A bend may reflect the overall shape of the dark matter halo. A narrow gap could have been produced by an encounter with an unseen concentration of mass, though other explanations must be considered carefully. Nothing about this measurement is simple. The Milky Way is not a static sphere. It has a rotating disk, a central bar, spiral structure, satellite galaxies, and massive companions that disturb its halo. The Large Magellanic Cloud, in particular, is heavy enough to influence the motions of objects across a wide region. A stream's present shape may contain the effects of several gravitational sources layered together. The cluster itself also contributes uncertainty. Stars do not all escape at the same moment or with the same speed. Binary encounters, internal relaxation, and changing tides influence when each member leaves. A stream is therefore both a map of the galaxy and a history of the cluster's gradual dissolution. This is one reason precise stellar motion matters so much. A still image shows where the stars are now. Proper motion adds the direction they are crossing the sky. Radial velocity supplies movement along the line of sight. Chemical abundance helps identify stars that may have formed together. When these measurements agree, a faint line of stars can emerge from what first appeared to be an unrelated field. Gaia transformed this work by mapping positions and motions across the sky. with consistent precision, making it possible to trace many coherent structures in the halo that earlier surveys could only partly reveal. The halo now appears less like a smooth cloud and more like a region crossed by remnants, streams, and fragments left by the Milky Way's long assembly. ecosmos.ioase.int2. Some of those streams came from globular clusters, others came from dwarf galaxies. The distinction matters because a dwarf galaxy can contain dark matter, gas, multiple episodes of star formation, and a wider range of chemical composition. A globular cluster is usually more compact and chemically constrained, though its multiple populations add complexity. By comparing width, motion, chemistry, and stellar content, astronomers can often infer what kind of parent system was disrupted. Sometimes the two histories meet. A dwarf galaxy may enter the Milky Way, carrying its own globular clusters. As the dwarf is stripped apart, its field stars spread into a broad stream, while some clusters remain recognizable. The clusters continue along related orbits, surviving as compact pieces of a galaxy that no longer exists as a separate body. The Milky Way's halo contains evidence of several such accretion events. Clusters associated with the same ancient merger may share orbital properties or chemical traits. Grouping them is difficult, and proposed memberships can change as measurements improve. Still, the general picture has become clear. Not every globular cluster was born within the main body of the Milky Way. Some are immigrants from galaxies consumed long ago. Their present locations may offer little hint of that origin. A cluster can now pass through a region far removed from the dwarf galaxy that carried it in. The parent system may have been dispersed so thoroughly that only a stream of stars and a few surviving clusters remain, yet their motions retain a connection. This is galactic archaeology in its most literal astronomical form. There is no buried city to uncover. The artifacts are still moving. They circle the Milky Way, crossing the disk, entering the halo, and returning along paths shaped by encounters that occurred before the Sun existed. A cluster's orbit is therefore more than a route. It can suggest where the cluster came from, how the galaxy grew, and how much mass lies between visible structures. Its stripped stars can reveal how the Milky Way pulls across thousands of light years. Its survival can show how tightly it was bound and how severe its passages through the galaxy have been. Not all clusters will survive indefinitely. Some are massive and compact enough to endure for many billions of years more. Others are already diffuse, losing stars with every orbit. Over time, the weakest may dissolve completely into the halo. Their stars will continue around the galaxy, but the cluster as a recognizable object will be gone. The disappearance would not be sudden. The core would grow smaller. The tails would lengthen. More stars would cross the tidal boundary and join the surrounding stream. Eventually, the remaining concentration might become difficult to distinguish from the trail it created. Nothing would explode. No final light would mark the ending. A stellar system that had remained bound since the early Milky Way would simply cease to be a cluster. There is a generational thread hidden in that long unraveling. Early observers saw rounded patches of light and gave them places in star catalogues. Later telescopes separated their outer members. Photographic surveys revealed wider structure. Modern astrometry now follows motions so small that the escaping stars can be connected across great spans of sky. Each generation receives the same ancient systems with a little more of their motion made visible. Tonight, a globular cluster may still look complete through an eyepiece. Its center is bright, its outline balanced, and its stars appear gathered into one enduring form. Beyond the field of view, however, some of its former members may already extend along the orbit, like a memory too wide for the telescope to hold at once. The cluster travels on, carrying its oldest stars through a galaxy that is still reshaping it. And behind that compact sphere, the Milky Way leaves a trail written in stolen light. Some globular clusters seem to belong to the Milky Way as deeply as its oldest stars. Others move as though they remember another home. The difference is not visible in a simple photograph. Quite, two clusters can appear almost identical through a telescope, each a rounded concentration of old light, each filled with stars that formed billions of years ago. yet their chemistry and motion may tell separate stories. One may have formed within the young Milky Way. The other may have arrived inside a smaller galaxy that no longer exists. To separate those histories, astronomers compare several clues at once. Age is one clue, metal content is another. Orbit adds a third. The detailed abundances of individual elements can provide still more information, because stars born in different environments are enriched at different rates by earlier generations of stellar activity. A cluster moving in the same general direction as the galactic disk may have formed within the early Milky Way, though orbit alone is never enough to prove that origin. A cluster on a highly tilted, elongated, or backward-moving path may be more likely to have entered through a merger. Chemical patterns can strengthen the case. Small galaxies often form stars less efficiently than large ones. Their gas can remain poor in heavy elements for longer periods. A globular cluster born inside such a galaxy may therefore have a different relationship between age and metallicity than one formed in the rapidly growing main body of the Milky Way. When many clusters are placed together on an age-metallicity diagram, patterns begin to emerge. Some follow a sequence consistent with early formation inside the Milky Way. Others appear along branches that may reflect slower chemical development in smaller systems. These branches are not labeled by nature. Astronomers must compare them with orbital families, stellar streams, and models of galactic assembly. The result is not a perfect family tree. It is more like a set of overlapping traces, some clear and others faint. The early Milky Way was not a finished spiral galaxy waiting to receive its first globular clusters. It grew through the gathering of gas, dark matter, stars, and smaller galaxies. Its central regions developed while satellites entered from different directions. Some were absorbed quickly. Others survived for billions of years before tidal forces pulled them apart. Globular clusters were carried through this process like dense seeds embedded in larger systems. A dwarf galaxy could lose its outer stars first. Those stars would spread along the orbit and become part of the halo. Its inner regions might remain bound for a time, continuing around the Milky Way as a shrinking remnant. Its globular clusters, compact enough to survive the stripping, could separate from the parent galaxy and continue on their own. Long after the dwarf itself became unrecognizable, its clusters might remain. This helps explain why the Milky Way's globular cluster system is not one uniform population. It is a mixture assembled over time. Some clusters probably formed in the galaxy's earliest central regions. Some may have developed as the thick disk and inner halo took shape. Others arrived in mergers from beyond the original Milky Way. Their present locations do not necessarily show where they began. A cluster now passing near the galactic center may once have belonged to a satellite. Another in the outer halo may have formed within the Milky Way and later been pushed onto a wider orbit. The galaxy has had billions of years to rearrange the evidence. Even so, certain clusters stand out. Omega Centauri is the most massive globular cluster associated with the Milky Way. It contains several million stars and shows a broad range of stellar metallicities, more varied than the patterns found in many ordinary globular clusters. Its multiple populations suggest a long and complicated history. Because of this complexity, astronomers have proposed that Omega Centauri may be the remaining nucleus of a dwarf galaxy whose outer stars were stripped away by the Milky Way. A galactic nucleus is a special environment. It sits at the deepest part of a small galaxy's gravitational well, where gas can collect and star formation may occur across more than one period. If the surrounding galaxy is later, it means this nucleus can survive as an object that resembles a massive globular cluster while preserving a more extended chemical history. The idea fits several features of Omega Centauri, but its precise origin remains an area of continuing study. The cluster may preserve the central remnant of an accreted system, yet reconstructing that system requires linking chemistry, age, motion, and simulations of the merger that brought it in. Another object, Messier 54, offers a clearer view of the connection between globular clusters and galactic nuclei. Messier 54 lies in the direction of the Sagittarius dwarf spheroidal galaxy, a satellite currently being disrupted by the Milky Way. It occupies the central region of that system and is often discussed as a nuclear star cluster associated with the dwarf galaxy. The Sagittarius galaxy has been stretched into enormous stellar streams that wrap around the Milky Way. Its stars are being added to the halo, while several globular clusters have been linked to the same accretion event. Here, the process is not only ancient history, it is still unfolding. The dwarf galaxy has not yet disappeared completely. Its streams remain coherent enough to trace, and its surviving clusters still reveal their relationship to the larger system that carried them. This gives astronomers a working example of how the Milky Way may have gained some of its older clusters in the distant past. Other merger remnants are harder to identify. Their parent galaxies dissolved long ago, and their stars now overlap with populations from separate events. Researchers assign names to some of these ancient structures so they can discuss their likely components. But the boundaries are not always final. One reconstructed merger appears to have contributed a large population of halo stars on strongly elongated orbits. Several globular clusters have been proposed as members of that same event. Other clusters may be connected with different accreted systems, each representing a smaller galaxy that entered the Milky Way on its own path. The details continue to change as measurements improve. A cluster once assigned to one merger may later be moved to another group. An orbital match may weaken when a more precise distance becomes available. Chemical evidence can confirm a relationship or reveal that two objects with similar motions formed in different environments. This uncertainty does not erase the larger picture. It shows how difficult it is to reconstruct a galaxy from surviving fragments. Imagine trying to understand a river's history from a handful of stones carried downstream. Each stone contains some record of its origin, but the current has moved it far from where it entered the water. Some stones came from nearby banks, others traveled from distant tributaries. Their present positions alone cannot tell the whole story. Globular clusters are more informative than stones because their stars can be measured individually. Yet they have also been carried by a moving gravitational system, and that motion has blurred the map of their beginnings. The galaxy itself has changed around them. Its disk grew more massive, its central bar developed. Satellite galaxies disturbed the halo. The Large Magellanic Cloud altered the motion of distant objects. Repeated passages changed cluster orbits, while tidal stripping reduced cluster masses. To move backward through all of that requires models. Astronomers build numerical versions of the Milky Way and allow virtual clusters to travel through them. They test whether an orbit could connect a cluster with a known stream. They examine whether a proposed dwarf galaxy could have delivered several clusters together. They compare the simulated debris with the positions and velocities measured today. No single simulation recreates every detail. The purpose is to find histories that remain consistent with the evidence. Chemistry provides a second path backward. Iron abundance reveals part of the enrichment history, but other elements add more precision. Some are produced mainly by massive stars and released quickly through supernovae. Others arrive later from lower mass stars or from different kinds of stellar explosions. The balance among these elements can reveal whether a system formed stars rapidly or over a longer interval. A large galaxy can enrich its gas quickly because it contains many stars and can retain more of the material they release. A small galaxy may lose gas more easily and may take longer to build the same abundance of heavy elements. The stars of a globular cluster inherit that history. Their surfaces become samples of gas that existed before the cluster formed. When astronomers spread their light into spectra, absorption lines reveal which elements are present. Those lines are narrow interruptions in the starlight, but together they contain the chemical environment of a galaxy that may have vanished billions of years ago. At this moment, the cluster itself may be moving far above the Milky Way's disk. Its parent galaxy may be gone. Its original gas cloud may have dispersed before the sun began to form. Yet the proportions of magnesium, silicon, calcium, iron, and other elements can still be measured in the atmospheres of surviving stars. The record is incomplete, but it is not silent. The most useful clusters are often those that can be placed within a wider family. A single unusual orbit may have several explanations. Several clusters sharing related ages, chemistry, and motion create a stronger pattern. If a stellar stream follows the same general path, the connection becomes more persuasive. In this way, the Milky Way's growth can be reconstructed cluster by cluster. The galaxy did not acquire all of them in one era. Some were already old when they entered. Others may have formed during periods of intense star formation triggered by early mergers. A few massive clusters could be the surviving centers of galaxies that once held millions or billions of additional stars. What we call a globular cluster may therefore describe more than one kind of origin. Some are true clusters formed as compact stellar populations. Some may be stripped galactic nuclei. Some occupy a boundary between those categories, shaped by conditions in the early universe that are difficult to reproduce in nearby space today. Their rounded appearance hides those differences. From Earth, each one can seem self-contained, as though it has always existed in its present form. But the stars inside carry memories of larger structures, and the orbit around them carries the influence of vanished companions. The Milky Way's halo is filled with such fragments, not ruins in the ordinary sense, because they are still alive with nuclear fusion, stellar evolution, and gravitational motion. They are surviving systems, altered but not erased. Through them, the early galaxy appears less like a single object being built in isolation, and more like a gathering of many histories. Some histories dissolved into streams, some settled into the halo, and some remained bound inside ancient cities of stars. Globular clusters do more than preserve the early history of the Milky Way. They also provide places where the laws of stellar evolution can be tested across hundreds of thousands of related stars. A single star offers only one life in progress. Its mass can be estimated, its temperature measured, and its spectrum examined, but its earlier stages are gone, and its later stages have not yet arrived. A globular cluster places many different stages side by side. The stars began under broadly related conditions, yet their small differences in mass have carried them onto different paths. Some remain on the main sequence, others are crossing the subgiant branch, their cores changing as hydrogen becomes exhausted. Red giants have expanded until their outer layers reach many times the diameter they once had. Horizontal branch stars are burning helium in their centers. Farther along, stars lose their outer envelopes and move toward the compact state of a white dwarf. The cluster becomes a long stellar lifetime displayed all at once. This does not mean every phase is equally easy to understand. The late stages of low-mass stars depend on processes that are difficult to observe directly. Material can mix between layers. Stellar winds can remove part of the outer atmosphere. Rotation, magnetic fields, and chemical composition can alter how a star changes. A model that reproduces one section of a color magnitude diagram may still struggle with another. Globular clusters reveal those differences with unusual clarity. If a model predicts that stars of a certain age and composition should gather in one region of the diagram, but observations place them somewhere else, the mismatch cannot be hidden inside the uncertainty of one isolated object. Thousands of stars show the same pattern. The horizontal branch is especially valuable. After a low-mass star climbs the red giant branch, helium begins fusing in its core. The star then settles into a more stable stage, but its temperature and color depend on more than age alone. Metal abundance matters. Helium content matters. The amount of mass lost during the red giant phase matters. Two clusters with similar ages and iron content can still have very different horizontal branches. This long-standing puzzle became known as the second parameter problem. Metallicity was clearly one important factor, but it was not the only one. Age, helium abundance, cluster density, and other properties have all been investigated as additional influences. There may not be one second parameter. Different clusters may reach similar appearances through different combinations of conditions. The question itself reflects how much detail is hidden inside a line of stars on a diagram. What appears to be a simple band of blue and red points may contain the effects of internal chemistry, mass loss, and billions of years of cluster evolution. Among the horizontal branch stars are objects that do not shine at a constant brightness. Their light rises and falls in a regular cycle. Many of these are R Lyrae variable stars, old pulsating stars found throughout the Milky Way's halo and in numerous globular clusters. Their outer layers expand and contract, changing the amount of light they release. The cycle can last less than a day, yet it has been repeating through a large part of the star's present evolutionary stage. The pulsation is not random. The brightness, period, and chemical composition of an R Lyrae star are connected closely enough that astronomers can estimate its true luminosity. Once the true luminosity is known, it can be compared with how faint the star appears from Earth. The difference provides a measure of distance. Globular clusters containing R Lyrae stars therefore helped astronomers map the scale of the Milky Way. Early in the 20th century, clusters appeared to gather around a point far from the Sun. Their distribution showed that the solar system was not near the center of the galaxy. The Milky Way extended far beyond the region visible as a bright band in the night sky, and its central concentration lay in the direction of Sagittarius. Dust obscured much of that inner galaxy, but globular clusters rose above and below the disk where they could still be seen. Their positions traced a much larger structure. The conclusion changed humanity's location within the Milky Way. The Sun was no longer near the center of a modest stellar system. It occupied the disk at a considerable distance from a galactic center, surrounded by old clusters. The clusters had been orbiting that center long before anyone knew where it was. Variable stars remain useful today, though distance measurement now combines many methods. Parallax provides geometric distances for nearby objects. Stellar modeling and variable star relations extend the scale farther. Each step is checked against others because a small error in distance affects the inferred luminosity, age, mass, and structure of the cluster. Even the most familiar globular clusters have required repeated revisions as instruments improved. A better distance can shift the estimated age. A more accurate measurement of dust can change the colors assigned to the stars. Improved chemical abundances can alter the stellar models used for comparison. The cluster does not change, but the interpretation becomes more precise. For a time, globular cluster ages created a serious problem. Some early estimates made the oldest clusters appear older than the universe allowed by the cosmological measurements then available. That could not be true. A cluster cannot form before the universe exists. The disagreement signaled that at least one part of the scientific picture was incomplete. Distances were revised, stellar models improved, measurements of the universe's expansion became more accurate. Evidence for an accelerating universe changed cosmological age estimates. The conflict gradually eased, bringing the oldest clusters into agreement with a universe roughly 13.8 billion years old. This episode in astronomy was not a failure of measurement. It was an example of separate fields pressing against one another until their assumptions became visible. Stellar evolution, distance calibration, and cosmology all had to fit within one history of the universe. Globular clusters still help test that history. Their oldest stars establish a lower limit on the age of the universe. The universe must be older than the stars it contains, with enough time allowed for the first generations of matter to gather, cool, and form the systems that became clusters. The difference between the age of the universe and the ages of the oldest clusters contains part of the interval between the beginning of cosmic expansion and the formation of the earliest surviving stellar systems. That interval is not known from one cluster alone. Astronomers compare many clusters, examine uncertainties, and use different methods of age estimation. White dwarfs provide one of those methods. A white dwarf no longer produces energy through sustained nuclear fusion. It shines mainly because it is still hot from the earlier life of the star. Over time, it radiates the heat into space and cools. The coolest white dwarfs in a cluster have been fading for the longest time. By measuring the white dwarf cooling sequence and comparing it with theoretical models, astronomers can estimate how long ago the first white dwarfs formed. When the earlier lifetime of their progenitor stars is added, the result offers an independent age for the cluster. The method carries its own uncertainties. White dwarf interiors are dense. Their cooling depends on composition, crystallization, atmospheric properties, and how efficiently energy escapes. Yet the agreement between white dwarf ages and main sequence, turnoff ages, strengthens confidence in both. Each method listens to a different part of stellar life. The turnoff measures which stars are only now exhausting core hydrogen. White dwarfs measure how long the remnants of earlier stars have been cooling. Variable stars help establish distance. Spectra reveal chemistry. Proper motions show membership and internal dynamics. A cluster becomes reliable through the overlap of these separate readings. Modern telescopes can follow stars deep into crowded cores and far down the faint end of the main sequence. Infrared observations can penetrate dust toward clusters near the galactic center. Ultraviolet light highlights hot horizontal branch stars and compact stellar remnants. X-ray observatories reveal close binaries and accreting objects. Radio telescopes time pulsars hidden among the visible stars. No single wavelength contains the whole cluster. Visible light shows the familiar sphere, but other forms of radiation reveal populations that would otherwise remain absent from the picture. A cluster that looks calm in an optical image may contain intense interactions in its core, rapid pulsars, hot accretion disks, and compact remnants moving among ordinary stars. The apparent stillness belongs to distance. The physical system is active at every level. Even the faintest stars matter. Low-mass red dwarfs can survive far longer than the current age of the universe. Many will continue fusing hydrogen after bright stars have become remnants. Because they are faint, they are difficult to detect at large distances, especially in crowded regions. Yet they hold much of the cluster's remaining stellar lifetime. The bright red giants draw the eye, but they occupy a brief phase. The smaller stars beneath them are more numerous and more enduring. They formed in the same remote era and have changed far less. In that way, a globular cluster contains two kinds of age at once. Some stars reveal time through transformation, others reveal it through persistence. Astronomers read both. They use the stars that are leaving the main sequence, the remnants that are cooling, the variables that are pulsing, and the low-mass stars that are still burning almost as they did near the beginning. Across these different lives, the cluster becomes a common reference point between the early Milky Way and the physics operating inside stars today. The archive is old, but it is still running. For a long time, globular clusters seemed like unlikely places to search for planets. Their stars are old and often poor in heavy elements. Their cores are crowded. Stellar passages can disturb wide planetary orbits. The most massive stars from the cluster's youth ended their lives billions of years ago, leaving behind radiation, stellar remnants, and a long history of gravitational rearrangement. From this, it was easy to imagine that planetary systems would either fail to form or fail to survive. The real picture is less certain. Planets are built from material heavier than hydrogen and helium. Rocky worlds require elements such as silicon, magnesium, iron, and oxygen. Gas giants also appear more frequently around stars rich in heavy elements, at least in the populations studied near the Sun. Many globular clusters contain far less iron than the solar neighborhood. This does not mean they contain none of the ingredients needed for planets. Even metal-poor stars formed from gas that had already been enriched by earlier generations. The question is whether enough solid material could gather into disks, grains, planetesimals, and eventually worlds. There is no simple metallicity line below which planet formation must stop. Small rocky planets appear to form across a wider range of stellar compositions than large gas giants. A cluster with little iron might therefore produce planetary systems different from our own, rather than no planetary systems at all. The environment adds another layer. A young star begins with a disk of gas and dust. In a dense cluster, nearby massive stars can heat and erode that disk with ultraviolet radiation. Passing stars can disturb its outer regions. These effects are strongest early, when the cluster is still forming and its largest stars remain alive. Yet, globular clusters are not equally dense everywhere. A star born near the outskirts may experience a much calmer environment than one born in the core. Even near the center, the actual risk depends on the distance of the closest passages, the size of the planetary system, and the changing density of the cluster through time. A tightly orbiting planet can be difficult to remove. The closer a world travels to its star, the more strongly the two are bound. A distant comet cloud may be stripped easily, while a compact inner system could survive many encounters. A passing star might tilt an orbit or alter its shape without ejecting the planet completely. The outcome is not always destruction. Some encounters may exchange planets between stars. A world could be pulled from one system and later captured by another, though permanent capture is difficult. Other planets may be released into the cluster and continue moving without a host star. These possibilities are supported mainly by gravitational models rather than direct observation. The distances are too great, the stars too crowded, and the planets too faint for a complete census. Astronomers have searched in several ways. A planet passing in front of its star produces a small reduction in starlight. This transit method has found thousands of planets elsewhere in the galaxy. But a crowded globular cluster creates special problems. Light from neighboring stars can blend together. The stars may be faint. Only a small fraction of planetary orbits align so that a transit is visible from Earth. One major search in the cluster 47 Tucanae looked for close-orbiting giant planets and found fewer than expected from comparisons with the solar neighborhood. The results suggested that either such planets were uncommon in the cluster, difficult to preserve, or less likely to form in its metal-poor environment. But the search addressed one type of planet on one type of orbit. It could not rule out smaller rocky worlds, planets farther from their stars, or systems in less crowded parts of the cluster. A non-detection narrows the possibilities without closing them. Other forms of evidence have shown that planets can survive in globular clusters. One of the most unusual examples is a planet orbiting a binary system containing a pulsar and a white dwarf in Messier 4. The system has a complicated history involving stellar evolution and gravitational encounters, yet the planet remains. Its existence does not prove that planets are common in globular clusters. It proves that survival is possible. The planet may have formed around a star that later became part of the present system, or it may have been captured during an encounter. Either way, it has endured a setting that once seemed too disruptive for long-lived planetary motion. This single system changed the question. Instead of asking whether globular clusters can contain planets at all, astronomers could ask what kinds of planets they contain, where those planets are most likely to survive, and how their histories differ from systems born in the galactic disk. The answer may vary from cluster to cluster. A dense metal-poor cluster with a collapsed core may offer different conditions from a looser cluster in the outer halo. A massive cluster capable of retaining gas early in its history may not resemble a smaller system that lost most of its original stars. Even within one cluster, the center and the outskirts are separate environments. Near the core, a planetary sky would be filled with nearby stars. Some would move enough across the background to alter familiar patterns over relatively brief astronomical spans. The nearest bright points might change position noticeably across generations, while the cluster as a whole continued its orbit around the Milky Way. Farther out, the sky would be less crowded. From a planet there, the cluster's center might appear as a luminous gathering across part of the night, a concentration of stars brighter and denser than the Milky Way appears from Earth. The rest of the sky would open toward the galactic halo. Whether such a world could support life is a different question from whether it could exist. Old cluster stars have had billions of years for biological processes to unfold, but long time alone is not enough. A stable orbit, suitable chemistry, persistent energy, and a tolerable radiation environment would all matter. Low-mass stars can live for immense spans of time. Around them, the habitable region lies close to the star. A planet there would be strongly bound and therefore more resistant to distant gravitational encounters. But low-mass stars can also be active, especially when young. Close planets may become tidally locked. Their atmospheres can be altered by flares and stellar winds. None of these factors gives a universal answer. The idea of life spreading between stars has also been considered. In a dense cluster, neighboring systems are closer together than stars near the Sun. Material ejected from one planetary system might have a greater chance of reaching another. Rocks carrying complex chemistry, or in more speculative discussions, microorganisms, could cross those smaller distances more easily than they would in the solar neighborhood. This possibility is known as panspermia, when it involves the transfer of life or its precursors. No evidence shows that such transfer has occurred in a globular cluster. The idea remains hypothetical. Ejected material must survive radiation, cold, time, and the violence of arrival. A shorter distance improves one part of the journey without solving the rest. Still, globular clusters provide a useful setting for asking how distance changes biological possibilities. Around the Sun, the nearest star lies more than 4 light-years away. In a cluster core, the distance between neighboring stars can be much smaller. If inhabited planets existed there, they might not be separated by the same scale of isolation. Their inhabitants would also see the universe differently. The bright cluster sky could make distant astronomy more difficult from the ground. A dense field of nearby stars would fill images and complicate the search for faint galaxies beyond them. Interstellar travel, however, would require shorter journeys between neighboring systems. This remains imagination constrained by physics, not a prediction. We do not know whether any globular cluster contains life. We do not yet know how common its planets are. We cannot assume that age creates habitability or that crowded skies create companionship. What the clusters offer is a wide range of natural experiments. They test planet formation with little heavy material. They test orbital survival under repeated stellar encounters. They test whether compact systems can endure while outer planets are stripped away. They preserve stars old enough to have hosted planets long before Earth formed. And they remind us that the solar system is only one arrangement among many. Here, planets circle a solitary star in a relatively open region of the galactic disk. Elsewhere, a world may orbit beneath a sky crowded with suns, inside a cluster older than nearly every structure around it. We have not yet seen such a sky directly. For now, it remains hidden inside unresolved points of light, waiting for instruments capable of separating the faint signatures of planets from the oldest cities in the Milky Way. A globular cluster can survive for most of the age of the universe and still remain unfinished. Its stars continue to move. Its center continues to exchange energy with its outskirts. The Milky Way continues to pull at the cluster from every side, and each orbit carries the system through another cycle of compression, escape, and gradual loss. Nothing about this future requires a sudden event. For many clusters, the ending will be a long reduction. Low-mass stars will continue to drift toward the outer regions, where the galaxy can remove them more easily. Tidal tails will lengthen. The central population will grow more dominated by compact remnants and tightly bound binaries. Encounters will send some stars outward and draw others into new partnerships. A cluster that now contains hundreds of thousands of stars may one day contain only a fraction of that number. The process can take billions of years. Massive, compact clusters may remain recognizable far into the future. Looser clusters on destructive orbits may dissolve sooner, especially if they pass repeatedly near the galactic center or through the disk. The precise outcome depends on mass, density, orbit, binary population, and the changing gravitational environment of the Milky Way. The galaxy will also shrink. Its stars will age. Its spiral structure will shift. Satellite galaxies will continue to interact with it. Over immense timescales, the Milky Way and Andromeda are expected to merge, combining their stellar populations into a larger galactic system. Globular clusters from both galaxies may survive that event. The galaxies themselves will not collide like solid objects. Their stars are separated by distances so large that direct stellar impacts will remain rare. But their gravitational fields will reshape one another, stretching streams, altering orbits, and redistributing clusters through the merged halo. Some clusters may be thrown onto wider paths. Others may sink closer to the new galactic center through repeated gravitational interactions. A few could be disrupted. Many may continue as recognizable systems, carrying the chemical and dynamical histories of galaxies that no longer exist in their current forms. By then, the Sun will have changed beyond recognition, yet the oldest low-mass stars in globular clusters will still be burning hydrogen. Red dwarfs consume their fuel so slowly that their expected lifetimes extend far beyond the universe's present age. Long after stars like the Sun have become white dwarfs, these small stars may remain active. The bright appearance of a cluster will gradually change. Red giants will continue to appear as stars leave the main sequence, but the masses reaching that stage will become smaller. White dwarfs will accumulate. Neutron stars and black holes will remain in the center or be ejected through encounters. Some binaries will merge, others will become wider or be broken apart. The cluster will grow dimmer as its remaining stars become less massive and less luminous. Eventually, stellar evolution and gravitational escape will remove the features that make the cluster familiar today. There may be no bright giants left to outline its shape. The surviving population may consist largely of red dwarfs, white dwarfs, neutron stars, black holes, and cold planetary bodies. The cluster may still be held together, or it may already have dissolved into the surrounding galaxy. Once a cluster is gone, its stars do not disappear. They continue along related galactic orbits, spreading farther apart with every passage. Their shared origin becomes more difficult to recognize, but traces may remain in chemistry and motion. A future astronomer, studying a sparse stream of old stars, might reconstruct the cluster after its shape has vanished. The system would survive as evidence rather than as an object. This has likely happened many times already. The globular clusters visible today are not a complete record of everything that formed in the early Milky Way. They are the survivors. Other clusters may have been disrupted by tides, internal evolution, or the mergers that assembled the galaxy. Their lost stars now move among the wider halo. The Milky Way may contain the remains of ancient clusters that no telescope can photograph as spheres because the spheres no longer exist. This changes the way the surviving clusters can be viewed. They are not permanent by nature. They are durable because of the balance they have maintained so far. Their stars began close enough together and their gravity was strong enough to resist dispersal across a span of time almost as long as the history of the universe. Every cluster that remains has passed through billions of years of selection. It survived the deaths of its most massive stars. It survived the loss of gas. It survived passages through the galaxy. It survived internal relaxation, binary encounters, tidal stripping, and the slow escape of members from its edge. Its present shape is the result of everything it has lost. From Earth, that shape still appears complete. A telescope gathers light from stars on the near side, the center, and the far side, compressing them into one rounded glow. The image contains no visible sign of how much mass has already escaped or how many earlier structures have been erased. It gives the cluster a kind of stillness that the cluster itself has never known. Inside, stars continue to cross the core. Remnants move, among them unseen. Binaries tighten. Outer members approach the tidal boundary. The entire system follows an orbit through the Milky Way that no human lifetime could observe from beginning to end. And yet, enough of that motion can be measured to reconstruct the larger story. A slight shift in position reveals the direction of travel. A spectrum reveals chemistry formed in an early galaxy. A color magnitude diagram records stellar age. A tidal stream shows where the Milky Way has been pulling. Each measurement is small. Together, they reach back toward the formation of the galaxy itself. Globular clusters began as dense gatherings of young stars in a universe with fewer heavy elements and less settled structure. Some formed within the growing Milky Way, Others arrived inside smaller galaxies. They aged while the galaxy assembled around them. Now they pass through the halo as compact witnesses. They show that the Milky Way was built from more than one history. They show how gravity reshapes a stellar population without erasing it. They show how stars born together can remain connected across almost the entire span of cosmic time. The clusters will not last forever, but forever is not required for them to carry the past. For now, their light continues to cross the halo. It leaves crowded cores, passes through the outer stars, and travels for thousands of years before reaching Earth. By the time it arrives, the cluster has already moved. Its stars have completed more of their orbits, and a few more members may have begun their departure. The image belongs to an earlier moment. The cluster remains ahead of it, still changing, and beyond the bright disk of the Milky Way, the oldest star cities keep circling,